And I tried to.
Was that okay?
Yeah, sure. And I try to keep it anyway kind of simple. I think most of you or everyone should know what a doubly robust estimator is. That's more about covariate selection than actually the estimation part. But you will see as a very simple toy example to walk you through the issues with basic and practice. So this is trying to work with Wei Chang Liu, a former student of mine. He's not the assistant professor at the University of Macau. And we have occasionally presented this during the last 1 year or 2 years before in different contexts.
Actually, we got, it's a little hard to hear. Let me see if I can get this one.
I can
try to hear it.
Yeah,
I want it to be able to hear. Okay, how's that? All right, go ahead.
Does it work? Okay, thanks. Okay, and we can do choice here with observational data where study participants will get assigned by administrators.
Sorry, sorry to interrupt. It sounds worse. Let me turn off.
Yeah.
So the audio. Let me try this.
I mean, I switched on my laptop. I switched off speakers and microphone, so there should not be feedback.
You can read pretty well. My computer's not plugged in.
Yeah, you're not plugged in. Okay,
good. So I'm not sure. Maybe is that mic is picking me up. So you could switch it over here, but your mic should be moving. No problem. We should take a minute to get it out.
Yeah.
So it's running off so Zoom is running off.
Yeah.
You're logged in. Okay, so we should make okay.
Yeah,
we should probably turn the audio here. Oh, you turn audio off. Here. Maybe just we forget that one. I'll just try not to. There's a mic out here.
Oh, there's a mic. Yeah.
People said they could hear me quite clearly. So let's try it. Yeah.
Can you hear me better? For you?
Let's talk a little louder.
Okay. So I can talk louder too. But I didn't talk a bit loud because I had a microphone before. So.
Yeah. Yeah.
Okay, 1, 2, 1, 2. Can you hear me? Okay,
how's the sound quality then?
Can you talk some more, Peter, so we can assess the sound quality? I can still hear Michael really clearly.
Okay, that's just my voice. Maybe you might have to give my talk.
We're gonna have Peter's gonna whisper in my ear, and I'm just gonna repeat. No, just kidding. Let's see. Yeah,
think-
sorry.
I think this is better.
Okay, I will just speak up a little bit more. Okay.
Let me get the you want live? Do you want to do a share screen? Or
Yeah,
share
I will
screen? Okay, great.
Okay. Let's see whether this works now. Okay, so we have a basic situation of an observational data set where study participants will self-select or get assigned by administrators or other persons into treatment and control conditions. And the issue with observational data is, as you well know, that the causal relations of interest that they're contaminated with confounding bias. So the main question is how to remove the confounding bias. First, we think about, of course, causal identification. It's a question about with the set of covariates that allow us to remove the entire confounding bias. And then the second step would be estimating the causal effect by a statistical adjustment. And you can think about regression adjustment, inverse probability of treatment weighting, or propensity scoring chain or stratification. So here's the toy example I'm going to use. Use a causal graph to explain everything. And so we have a treatment C and an outcome Y. And we have in this case some four baseline covariates U, E, M, and W. And here just an example. Later I will only use the variable names and not the example itself. But if you think about the treatment as math tutoring, whether the student takes math tutoring or not, then we have the outcome Y, which could be a math achievement score. And then we have a confounder W here, which is math ability. And then we might have a variable U, and the variable V is apparent income and current education. And we might use the two variables to compute socioeconomic status. And that would be a causal structure which we assume it's not realistic, it's just a toy example. As you will see, so in setup, there's one confounder and there's one collider verb in there. So the simplest possible causal structure you can think about how a data set is generated. Here I just assume that all the variables might be observed, but sometimes they might not be observed depending on which covariates you can select or cannot select. And this will then vary a little bit during the talk. So what we are interested in is the causal effect of the Z on the outcome Y. That's what our interest is. And we would like them to use conditioning adjustments or regression adjustments to estimate the average treatment effect. So besides regression adjustments, we can use inverse probability of treatment weighting based on the propensity score. But the talk will focus then mostly on doubly robust estimation, where we combine regression adjustment with inverse probability of treatment weighting. And the question I will focus on is, how should we select the covariates for a doubly robust estimate? Is it the same as for a single estimator, let's say regression adjustment, or inverse probability of treatment weighting? And particularly of interest is the situation then with high-dimensional data sets, because as you will see, I will focus on situations where I choose different covariates for the regression model and different covariates for the propensity score model. So we allow here for differential covariate selection, which is frequently done in practice with high-dimensional data sets. So not using the same covariates for both the regression and the propensity score model. Okay, so we'd like to identify the causal path or the effect of the causal path from Z to Y. And we have here one confounder path from Z to W to Y, which transmits confounding association because W simultaneously affects V and Y. And we have one collider path from Z to U to M to V to Y. And this collider path is naturally blocked by the collider M, so there is to begin with no association transmitted. Unless you conditional M, then there might be transmitted along this path. So the question is, to begin with, what are the valid adjustment sets that would block all the confounding association, and which covariate sets would actually fail to remove the confounding association? Okay, so we can use the adjustment criterion in order to assess which covariate sets work and do not work in blocking all the confounding path. And here is all the valid adjustment sets that block the confounding. I mean, the first one is just W, because W will succeed in blocking the confounder path, while the collider path is naturally blocked and does not permit any association. But you can, of course, combine W with U, because here the collider path remains blocked. W with V, you can also have W, U, and V, but you can also include W and M if you in addition either include U or V, because once you condition on a collider M, then you open the collider path, therefore you need to block the path either as U or V or both. Okay? So all the valid adjustment sets, of course, need to include W, right? Because we need to block, if you like, we need to block the confounder path at W. And then you have multiple choices what you want to do with U and M. You only need to make sure that you do not include M alone, because M would open a collider association and would include collider bias into your treatment. Okay, once you select it, or once you know which covariate sets actually work in removing the entire confounding bias, you can, for instance, use a regression estimator and could say, okay, let's choose the covariate set W and V. Right? W and V are natural choices. V is W because they are predictors of the outcome Y. So you use the predictors of Y to adjust for it. And here's just a very simple regression model where we regress Y on treatment Z plus then the covariate set A consisting of W and V. Yeah, just assume that the functional forms are simply linear. This talk is not about how to correctly specify the functional form. The talk is about how to correctly select the covariate. So just assume for simplicity and to keep the notation simple that a linear functional form is appropriate. From this regression, we can get the predicted values of the regression under the treatment is off and the treatment is on. So I have then a notation M, Z of A and beta, which I will use later when I formalize the doubly robustness property. Okay, M is then the regression function, just that you keep this in mind. And then we could alternatively, instead of a regression estimator, use an inverse probability of treatment weighting approach. And here I could choose a different covariate set, W and U, which is also a natural choice because the parents of Z is W and U, so they are predictive of treatment selection. And then again, here we could just use a logistic model to estimate the propensity score, and then I use the propensity score to estimate the weights for the average treatment effect, right? And then we use weighted least square regression to regress the outcome on the treatment indicator, and then I get the inverse probability of treatment weighted average treatment effect. So a doubly robust estimator just tries to combine the regression adjustment and the inverse probability of treatment weighting. And so what we do is we just run the regression with the selected covariates in there. And we use in addition inverse probability of treatment weighting. That's again a very naive approach because the treatment is not interacted with the predictors. So again, as I said, when we make a linearity assumption, and I refer to this estimate as inverse probability weighted regression, but there's probably a more famous class of doubly robust estimate called augmented inverse probability weighting, which you're probably all familiar with. But I will mostly talk about just inverse probability weighted regression. Simulation results show you the results for both doubly robust estimators. Okay, so what does the doubly robustness property say without formalizing it yet? So what we need is an observed set of covariates X that meets the adjustment criterion, which means it meets the unconfoundedness assumption, right? Then doubly robust estimators for the average treatment effect are consistent if at least one of the two models, either the regression model or the outcome model, is correctly specified. So we get two chances to get the model right. If one model is right, you would remove the entire confounding bias. Right, and that's, I assume most of you already learned about it, but it's actually a little bit tricky what this means, and that's what my talk is about. So when we say correct model specification, it has two components. You need to select the correct covariates, and in addition, you need to get the functional form specification, right? Again, in this talk, I assume we have no issues with the functional form specification, which let's say just linear. Therefore, I only focus on selecting the right covariates. So here's a question which we'll discuss now. Is double robustness guaranteed if one of the two models successfully removes the entire confounding bias on its own? Right? So one model really removes the confounding bias, but is this good enough to get a doubly robust estimate? So here's the first two examples out of 4. As you can see in the regression model, I condition on W and V. Okay, I would condition on W and V, and this is a valid adjustment set. I would block all the confounding. I would block the confounding association, and conditioning on V does not open the collider path. Therefore, the regression adjustment would be valid and result in an unbiased, in this case, unbiased average treatment effect. For the propensity score model,
sorry, but just for the some people in the causal inference group may already know, but do you want to just tell briefly what it means to be to have an estimator that's where all the confounding is removed, that it's a unbiased in the asymptotically, is that like the estimator will converge to the truth?
Correct. So if the regression assumptions hold, it would be unbiased. Otherwise, if a different estimator would be consistent.
Is it acyclic? Yeah. So it's the Yep. Great. Thanks.
So for the propensity score model, we condition on W and we condition on U. And also here, that's a valid adjustment set. Therefore, if you would use the inverse probability of treatment weighted estimator, you would also remove the entire confounding bias. So when we now combine both regression adjustment and inverse probability of treatment weighting, right? We can, of course, assume that we get a doubly robust estimate, meaning that the doubly robust estimate is consistent. And in this example, it actually is the case. Both models are correctly tested. So now let's look at a different situation where the regression model only conditions on W, which is a valid adjustment set because it blocks all the confounding association. But the propensity score model is misspecified. It would only include 2. But would fail to include the confounder W. Therefore, the inverse probability of treatment weighting estimator would not return a consistent estimator of the average treatment rate.
Can I just sort of talk with, like, have you talk about sort of the motivation for choosing different covariates for the outcome regression for the propensity score model? Is there? Does this happen often in practice? Is there an advantage to doing that? Or
yes, so the slide is coming up later.
Okay.
Because there are good reasons why we might do this, particularly if the data sets are very large. And I have an extra slide on it. Okay, thank you. But that's an important and good question. Right? Otherwise, you could say, why not using the same set of covariates for both? Right? And this will be, anyways, a recommendation for practice to avoid any issues we are running into. Right? So, in this case, our propensity score model is misspecified. The regression model is correctly specified. Now, when we combine the regression adjustment with the inverse probability of treatment weighting, we would assume that the doubly robust estimator actually is consistent, and it is. Okay. So now let's look at another example where we just flip the role of U and W. Now I'm conditioning my regression adjustment on U only, while the propensity score model conditions on the confounder W. Right? So now the regression model is misspecified, would result in a bias effect estimate, but the propensity score model is correct. Therefore, the inverse probability of treatment weighting estimator would be consistent. Now, when I combine the two in a doubly robust estimator, turns out it's biased. It's no longer consistent. Why? I mean, the idea is very, Yeah.
Okay, I don't want to.
The idea is very simple, right? So although the propensity model is correctly specified, and then the probability of treatment weighting estimator would remove all the confounding bias, and it does so, right? However, when you run a regression and condition on U alone, you have a bias amplification effect. The bias will be inflated. But the propensity model did not learn about the bias amplification factor in the regression model, because the propensity model was kept blind of the bias amplifying misspecification. Therefore, you will get a bias effect. Okay. The same you will see so for the fourth example, where the regression model is correctly specified because we condition on W. But the propensity score model is incorrectly specified because in addition to W, we now open the collider path and transmits collider association. So the regression adjustment would work well on its own, but when I combine it with the inverse probability of treatment weight, I induce collider association because the regression model was kept blind to the collider bias inducing misspecification of the propensity score model. So when we just say if one model succeeds in removing the anti-confounding bias is good enough, that's actually not true. You will see when we formally define the double robustness property, why this didn't work. We'll immediately see this, but usually we miss this when we look at the definitions and the proof of double robustness. Okay, so as we just saw, if one or sometimes even both models succeed in removing the anti-confounding bias, combining them into a doubly robust estimator does not guarantee that it removes the anti-confounding bias. Right? We could also formulate a different set. So let's assume I use a subset A and a subset B of X, and both A and B meet the adjustment criterion, which means they would on their own remove the anti-confounding bias. And then the question is double robustness guaranteed if the propensity score removes all the confounding bias using B, and the regression model removes all the confounding bias using A. In this case, when you combine it, there is no guarantee that you remove all the confounding bias with the double robust estimate. It's not a really very relevant case, but it can happen. So, and the final question is, does double robustness require that the propensity score and the outcome model must use the same set of covariates? Particularly if we look at the proofs of double robustness, you only see one covariate set X, and you might think you need to use the same covariates in both sets. No, you don't. It's not required, but it's getting tricky, right? And that's what I will try to show you why it's getting tricky. Okay, so it's the formal definition of the double robustness property. So we need a set of observed covariates X that meets the adjustment criteria. Okay, that's where we start. Then we have two subsets A and B. Right? A we use for a regression adjustment, B for the propensity score model. And then double robustness is guaranteed if, in addition to the adjustment criterion that is met with regard to X, that the regression function or the predicted values converge in probability to the conditional expectation function of the potential outcome, or that the propensity scores converge in probability to the conditional expectation function of the treatment indicator, right? So the crucial point here is that it's not good enough that A or B remove the anti-confounding bias on its own. They need, in addition, converge to the expectation conditional on X, not conditional on A. Right? And X is the entire set of covariates you start with. So if you do an incorrect selection, drop some predictive covariates of the outcome model, then you will not meet this assumption, even if the subset would still meet the adjustment criteria. Right? So that's what we're trying to relax. We will later no longer require that we use the entire covariate set of X. We just first select the covariates and then check whether the selected covariates meet the adjustment criterion for a doubly robust estimate.
Okay, so my understanding here. Yeah. So for the adjustment criterion is satisfied by X. Is it also satisfied by A alone or B alone? well or in?
It has to be, if, for instance, the outcome regression is correctly specified, then A, of course, has to meet the adjustment criterion too, right? So A, if the regression was the correct one, right, then A, of course, would also meet the adjustment criterion, otherwise it would not obtain the pattern, right? But in addition, you need to correctly specify the function, in addition to having the right set of. Right, so if you're familiar with the proofs of double robustness, you will never see an A or B in there, it's always an X in there. And how they would drop the covariates is that you can put restrictions on your regression parameters beta and gamma, you just force them to be 0. That's how we would drop the covariates.
Question. I see.
Oh, yeah, I see.
Yeah, I have a follow-up on the question that was just asked. So, if A satisfies the adjustment criterion, can't you just replace X with A throughout this definition? And uh, and then you would be guaranteed double robustness if um if if the outcome regression is correctly specified. Like I'm wondering, I see why um your facts hold, but I would have thought that it's because you need your two nuisance parameters to be functionals of the same set of covariates for the normal proof to run through, and not that you need um the yeah, does that make sense?
Sure. I mean, if you know to begin with that you will not use the anti-Z covariates of X, you could say, okay, I'm going to use A. And then you would make sure that A meets the adjustment criterion, and then you are good, right? But that's not what people typically do in practice. Particularly when you look at machine learning approaches, they use hundreds or thousands of covariates and will claim the number of covariates guarantees more or less that everything meets the adjustment criterion. But then we end up using the lasso, for instance, only with a small subset, right? And they run the lasso separately for the outcome model and for the propensities model.
I think I I'm missing a step in this second bullet because it seems to me that if A and B each, oh, I see, you do have the functional. I see. Okay, let me try this. I think that what's crucial in your letters A and B is that your regression functional and your propensity score functional converge in probability to functionals of the same set of covariates X. That's what's crucial here.
Exactly.
If they both ended up converging to functionals of A, that would be fine. And if they both ended up converging to functionals of B, that would be fine. But they have to be random. They have to be functionals of the same set of random variables.
Correct.
Okay,
Correct.
got it.
Correct. But the only thing is, if you then claim them, if they both converge to the same functional condition of A, then you would need to adjust your first criterion, right? Because it depends how you start. Everything for the doubly robust estimate, the property depends on which covariate sets you declare to meet the adjustment criteria. Right? I mean, you can of course adjust. You can say, okay, I don't start with the entire set X, I start with the subset. You can do so. But that's really what people do in practice. Right? They start with the claim that the entire covariate set meets the adjustment criteria, and then they do covariate selection and no longer check whether the subsets actually meet the adjustment. But that's at least what I typically see in practice. Okay. Yes,
So the covariates that you are choosing, maybe in X or are they like highly correlated? Because essentially the M function is just linear combination of those variables in A, right? And so are you assuming like if I take like a small subset of those variables, take a linear combination, it should span the space as what the space is spanned by?
Right. I mean, so you could, if for instance, X might contain a variable that is only predictive of the outcome, but is unrelated to, let's say, anything else, then you could remove it from A, but then on a condition A would get it. Condition A would not be met. Because if you miss a predictive variable in A here, you cannot converge to X, to a functional conditional. So we might still need the adjustment. But so when I then parse out some the assumptions later on with the double robustness criterion, then you will better see some how everything then works when you use differential covariates.
Can I just ask one more question?
Oh, sure.
So go back to Nancy's point about the conversion probably being conditional on the same set of covariates. Call that that X. Like if there are multiple sets that can satisfy the criterion, and you have like heterogeneity in the population, like does that sort of do you still run into problems there?
I mean, if you determine, I mean, later I will show you we can determine all possible sets that meet the double robust adjustment criterion. We can determine the entire sets that would work, right, based on graphical criteria. But then, even if you have effect heterogeneity in your population, it should not make any difference. Only the goal is to remove the confounding. If I correctly understood your question.
Yeah, I think I'm trying to figure out, like, what the statement is with regard to the subsets X, if there are like multiple things that could get you to the truth. Yeah. Like if they, right? So
yeah, there are. So the thing, as you will see later, is you can drop from X all the covariates that are not predictive of X given A. Those you can drop because then you will converge. Right? You can drop the non-predictive variables not in X again that are not predictive conditional.
So I propose that keep going.
Okay,
You keep saying, well, I'm going to X.
Yeah, right.
I want to give you that.
Okay.
Yeah.
Coming back to John's question of why.
Yeah, I want to see this. Really
why do we want to do differential covariate selection? And as I said, there might be situations where many more covariates than you have observations, then you're essentially forced to use subsets. And then doubly biased machine learning, it's common that you run a separate lasso on the regression model and a separate lasso on the propensity score model. So we'll end up having quite different sets of covariates here. But even if this would not be a case, there are efficiency considerations why you might want to use different sets A and B. For instance, if you want to include in your covariate set A any predictive variables Y in your regression model, because it would reduce the standard error, right? Even if it would not be needed to remove confounding, you want to nonetheless get an efficient estimator. And that's what the literature suggests. Include predictive variables in your adjustment set for a regression. On the other hand, with regard to the adjustment set for a propensity score model, you might want to exclude instrumental variables that are predictive of treatment selection but unrelated to the outcome Y, because they have a strong bias-amplifying potential. So you don't want to include them. So you might want to remove them, right? And it would automatically result in different covariate sets. And if you look at the very early examples given by Robbins and others, when they show a misspecification, they show the misspecification by choosing different covariates. Most examples show covariate selection issues rather than functional forms issues to demonstrate the double robustness. Okay. Okay, let me skip these slides and then we just go on to the extended double robustness condition and the adjustment criterion, and that's what the people essentially proposes. And so we start here with the covariate set X, which might be quite a large set of covariates, and then we use again a subset A for the regression model and a subset B for the propensity score model. But now we need a little bit more additional notation. We define A star as the minimal subset of predictive covariates, such that the probability distribution of Y, conditional on A and Z, of course, is the same as if we condition on A, which means we allow to drop, or we drop all the non-predictive variables, such that we end up with the minimum subset of predictive covariates. Later I will call this the Markov boundary, because everything else, all the covariates in A but not in A star, will be deseparated from the outcome Y, right? That's a minimal set of predictive covariates. You're allowed to drop what is not predicted. And the same we do for the propensity score model. B star is the minimal subset of predictive covariates with regard to the propensity score. And here's the condition in terms of the probability. And here's now the doubly robust criterion if you use different covariates for the regression and propensity score model. So we get a consistent doubly robust estimator if the union of A star and B star, the union of the minimal subset of predicted covariates, meets the adjustment criterion, and if one of the two doubly robustness conditions is met, now with regard to F and not with regard to X. So it's a much smaller set. Where now we have that the functional, the regression function converges in probability now to the conditional expectation function with regard to A. This is on the correct specification of the functional form. But in addition, require that the conditional expectation function conditional A is equivalent to the conditional expectation function conditional S. So either this condition must be met, or we need to get the functional form right with regard to the propensity score model and covariate set B. And the covariate set B must then guarantee that the conditional expectation function of Z is equivalent to the corresponding one, the conditional S. So the advantage of this formulation is first that it separates functional form specification, which is shown here under the convergence in probability, from covariate selection issues, which is formulated in terms of equivalence and conditional expectation, right? And S is typically a much smaller subset, a much smaller set than X overall, because often you will succeed in using smaller subsets to meet the adjustment. So the question then is, how can we actually choose in practice differential covariate sets, or test when you have different sets A and B, whether they meet the extended doubly robust adjustment criterion? And that's where we developed a doubly robust adjustment criterion. And now we switch on the notation and terminology, graph terminology, where we say, assume we have a deck with G that correctly represents the data during process with observed covariates X. And then we have adjustment sets A and B. These are subsets of X for the propensity score and outcome model. And then we let A star, not only definition, be the Markov boundary of Y, conditional on C and A. B star, the Markov boundary of C and B. So these are the minimal sets of predictive covariates. Then S is the union of the two sets. Then we need also, with regard to S, the union of the sets, the Markov boundary of Y, conditional on X and Z. And we need the Markov boundary of Z given X. So once we have this in place, then the double robust adjustment criterion can be formulated as follows. The union of A star and B star meets the adjustment criterion. And then at least one of the two equivalences in Markov boundaries holds. That the Markov boundary A star is equivalent to the Markov boundary of Y given S, what we call SY star here, or the corresponding Markov boundary with regard to the propensity. That's equivalent to the previous formulation. The only thing is, this can be used now to automatically determine all admissible covariate sets A and B. So you can implement it in a software package like Doubly, and then you can let Doubly find all the admissible covariate sets A and B. And I will show you now, again, coming back to the examples, a few examples where you see why now so we can determine whether the double robustness adjustment criterion is met or not met using the graphical criterion. Okay, so here's again the first example where we have W and V for the regression adjustment, W and U for the propensity score adjustment. And now we look at the union of the predictive sets. V is predictive of Y, W is predictive of Y, U is predictive of C, W is predictive of C. So therefore the union of all the predictive sets is W, U, and V. And this means the adjustment criterion, as we saw at the beginning. And then we can check some of the two conditions. whether the conditional expectation function of y given A is equivalent to the one given S. And as it turns out, since V and W here on the left-hand side are the predictive covariates, and the only one that is in addition here is U. But once I condition on V and W, U is no longer predictive of Y, therefore the condition is met. Right? The same we can do for the propensity score model, and also here U and W are predictive of Z, but including V does not make a difference because V is not predictive of T conditional on U and W. Right? So the doubly robust adjustment criterion would be met. Then when we have here the regression adjust for W, right, that's correctly specified, the propensity score model is incorrectly specified, then W is predictive of Y, U is predictive of Y. You might see this when, U is predictive of C, correct. That's the propensity score model, U is predictive of D. Therefore, the joint covariate set is W and U. W and U meet the adjustment criterion. The regression model meets the first condition of the DR adjustment criterion, but the second one, the propensity score model, fails to meet it, but only one of the conditions to be met, therefore it's doubly robust. So now we switch the covariates here. Now we use U for the regression model, W for the propensity score model. We get again the same. W and U are predictive of the outcome. You might wonder here, why is U predictive of the outcome Y? Just to briefly think about it. Why do I say U is predictive of the outcome Y?
So going through goes from pathway from C.
Yeah, so when we run this regression, we also condition on Z and A. So we condition on Z and A's analysis.
Condition.
And now, when I condition on Z, then Z is a collider where U and W pointing to Z. Therefore, I get essentially collider association between U and W. Therefore, U becomes predictive of the outcome Y. Therefore, U is predictive, and therefore U needs to go into my joint adjustments, right? Because it's predictive of Y conditional on Z. Okay. And W, of course, is predictive of treatment selection. So it goes into the joint set. The joint sets meet the adjustment criterion. But now when I look at my conditions A and B here, both are violated because in A, so I only condition on U here, but there's also W in the joint set. Therefore, and W is predictive of Y, therefore that's not equivalent. And the same can be shown for the propensity score model, and the DR adjustment criterion is not met. Okay. And the same you can show for the case where we have a misspecified propensity score model where we condition on the collider variable, induced collider bias. The issue then is that the joint set of predictive covariates is W and M, and this already fails to meet the adjustment criterion. While still, the second condition about the propensity score model would hold, but here the failure is due to the joint set missing the adjustment criteria.
I have a basic question. So I could have asked this many slides ago, but what would you say is the role of N in this graph?
So the role of M, so usually if you would know it's a pure collider, you would not condition on it anyways, if you were to know it. I mean, in practice, the situation is more tricky. It's often not a pure collider. M might be simultaneously a confounder, right? Then you have to condition it on it anyways. But the easiest way, M in this case, as an example, I used on socioeconomic status. Right? Socioeconomic status is computed from parents' income and parents' education. So it's a clear, strong collider variable because it's a deterministic computation. And you might not have, let's say, parents' income education observed, so you're forced often to condition on socioeconomic status. If it turns out, in this case, it would not be a confounder, but only a collider, then of course you put yourself in a bad condition to begin with. But you need to have the knowledge, otherwise it's very hard to determine what the pure collider is.
So U and V might be unobserved?
Could be unobserved.
But M is definitely.
M is definitely observed. Otherwise, we could not remove the confounding effect. Right? And so in this case, we have here, it could be that U and V is not observed, therefore an analyst might think, okay, when I include instead M, the socioeconomic status instead of parents' income and parents' education.
Okay, and in the previous slide, it was okay to condition on M, even though it is a collider? Can you catch that part?
Here we never condition on M.
I made that up. Okay, you would be.
But there are situations which I'm not showing here where you can condition on M.
Oh.
When you then you need to have at least U or V observed, and then you need to put it into the right equation. Otherwise, it wouldn't work.
So then the role of U and V, are they confounders or colliders?
No, neither. They're neither confounders. The only thing is there's one collider, right? And when I condition on M, I would open some this collider.
So I guess I was wondering then, why are we conditioning on U and V at all? Are they causing problems?
No, if you were to know the graph, you would never condition essentially on M, right? You would select W, and you would essentially do this model. You would select W and V for the outcome model, and W and U for the selection model. Now, this would be the selection you would choose if you were to know the graph. Here, it would not do any automatic conversion.
Oh, okay. Because when we do that, we are removing that zigzag pathway while not using colliders. Okay, thank you.
So I forgot that probably 250 combinations of covariates, and we evaluated all of them, whether the combination of covariates and once you get the doubly robust estimate and when you do not get. So you can evaluate all possible combinations. I show only some examples. So not to look at the example where we get collider association. So here we have the situation where regression is just for U, and the propensity model adjusts for W. So the regression introduces bias amplification, bias-specified amplification. To see this is the original bias is 0.299. So we have a bias about of 0.23. So if I run my regression only with U, we see that the bias slightly increases from 0.3 to 0.319. Okay. When I run my inverse probability weighting method to estimate the ATE, we succeed in removing all the bias. There's essentially no bias remaining. But when I combine both, and you have the AIPW and the weighted regression estimation, then we see a slight bias of 0.022 or 0.024, which is exactly the amplified portion of the bias. So we fail to remove the amplified portion of the bias because the propensity score model was kept blind to the bias amplifying misspecification of the regression model. Okay, you cannot independently specify the regression and the propensity score model. They depend on each other because the other model need to learn about the other model's misspecification. If we have the situation here with W in the regression model, it removes all the bias, no bias here. When we include the collider variable M here in the propensity score model, the APPW estimator would now have a negative effect of minus 0.14, quite a strong effect, which is not due to the open collider path, inducing negative collider association. When I combine both regression and the inverse probability weights, then the doubly robust estimator cannot deal with the induced collider association. Right? Again, because the regression model did not learn of the bias inducing this specification of the propensities. Right? And here other examples, maybe the last one is interesting, where we have the regression model is correctly specified, would remove the entire confounding bias. The propensity score model is correctly specified, would remove the entire confounding bias. When I combine them, you get bias. Right? That's a situation not very realistic in practice because it's very weird how you do the conditioning, would not occur to you in practice. But
Those, can you put in? Oh, there we go.
Okay,
See, this is great.
so we have now implications for practice. So the important aspect is, and that's what I already highlighted, is that the correctly specified model must not be kept blind from any bias-inducing misspecifications of the other model. Any misspecification that result in bias amplification or collider bias. So which means it's not a good idea to independently select the covariates for both models because they depend on the term. So issues with regard to covariate selection can be avoided if you use the same adjustment. Right? If you use the same adjustment set, you're good. We could use, for instance, the union of A and B, right? But you need to check whether A and B meets the adjustment criteria. There is no guarantee if X meets the adjustment criteria. You select subsets A and B. There is no guarantee that the union meets the adjustment criteria. So with large covariate sets that might not be desirable because new subsets A and B might still be very large, such that you might want to have differential covariate selection. And you might also avoid again some inflated standard errors by including essentially independent variables that only treatment selection. So you could, after the fact, select covariates, still try to remove a couple of covariates by theory, which, for instance, Farrell suggests one should do. You can do, but you need to be very careful what you are doing, because you might start with the result where the adjustment criterion is met, but then you might start introducing bias by removing or adding the wrong covariate. So therefore, differentially adding or dropping covariates must be done with great care. Ideally, you have a formalized, data joining process that has been formalized in a directed acyclic graphs. So where this also becomes quite relevant is these days in Doubly biased machine learning. If you use double lasso or the lasso for a treatment and the outcome model separately, you just need to assume that the entire covariate set X, let's say, does itself not meet the adjustment criterion, but there is one or multiple subset of X actually meet the adjustment criterion, and you might hope that the lasso will find the corresponding valid adjustment set. But that's not the case. Even if we use an ideal automatized covariate selection, they would find the Markov boundaries. Okay, so you have a perfect flexible model. You will find the Markov boundaries, but if you do not start with the covariate set X that meets the adjustment criterion, you might find incorrect subsets A and B that actually do not remove the entire confounding bias, meaning that the doubly robust estimate is not consistent. Right, and that's where one of my students and I are right now doing simulation studies to figure out how serious the issue actually. So, as a last comment, no matter how covariates are selected, researchers relying on differential covariate selection must carefully assess whether A and B meet the doubly robust adjustment criterion. Then make sure that the union of the covariates actually meets the adjustment criterion and not only a larger set where you start your machine learning procedure to begin. Okay, thank you very much.
Well, thank you for the talk. It was very interesting. And I open it up to questions. I have questions, but I'll wait. Good.
Yeah, thanks so much for the talk.
Please tell your name for so that
So I was just wondering if I might try to think about this as a subproblem of a broader question, when you're trying to combine different covariate sets when you're adjusting using two criteria for the same effect. So, for example, suppose that we're trying to identify an effect using both the front door and back door criteria. So in some ways, a lot of ways, it doesn't directly carry over. It seemed like adjustment here was just backdoor, but there might be some similar types of issues that arise.
I mean, that's a good question. I didn't think about other classification strategy than just covariate adjustment. Might be worth thinking about it. I didn't think about it. Might be interesting when you do, let's say, a conditional instrumental variable estimator, then you also need to select covariates under which the ID assumptions hold. Or if you do a TID estimator conditional with other covariates, you might also have similar issues in a, let's say, if you would think it a doubly robust estimator. But I didn't think about it. That's it.
Great. Other questions?
I have some questions, but I'm happy to defer to others first. I have a lot of questions.
Great. I think Helen, go ahead.
Oh, I popped my question in the chat in case you can't hear me. But this process of selecting S, the union of A star and B star, these minimal sufficient adjustment sets, is this process a sufficient criterion for consistency of the AIPW, or is it sufficient and necessary?
Yeah,
And
maybe I answer. It is sufficient but not necessary. Because when we look at the Markov boundaries for the outcome and for the treatment, we do not care about the causal structure between the two Markov boundaries, right? So you could do it a little bit more extreme and could find some additional solutions here. But we thought on, given that the subject matter theory about the covariance relation is usually not that reliable, it's better to just look at the Markov boundary so we are satisfied with the sufficient condition. It's not necessary.
got it. And if there are other ways, other like sufficient conditions, do we get efficiency gains from this particular sufficient conditions of considering S the union of A star and B star? Or is it just we haven't really come up with other sufficient conditions, so we can't really compare right now?
Yes, and here we focus only on what guarantees double robust covariate selection. But you can, if you have a causal graph, you can determine all the covariate combinations that work, and then choose the one that probably would deliver the most efficient estimate.
Thank you.
Well, I have a question about the. Have you heard of an estimation method called, I think it's called CTMLE, where the C is for collaborative. So it's I'm not involved in this at all, but this is Mark Vanderland and others have, they have an approach where it's building, trying to build up prediction models build up propensity score and outcome regression models, but collaboratively using both together. And I think that's in line with what you're saying. You can't do it separately, and it's gonna there's a risk if you just do it completely separately, those two things. But they have a way. I think they also appreciate that, and so they have a way of jointly building those two in a way that's trying to be parsimonious. So that it's not exactly the same as what you're talking about, but it's really. So
it's a good suggestion. I can look into this. I need to look into it.
I'll send you a link if you're interested. Right. I think it's CTMLE. There are multiple types of TMLE. So that, but I'll send. I think that's anyway related to this. And yeah, this important issue that you need to. Yeah, there has to be done together. Yeah, otherwise you get these issues. Right. And this, and also I think it points out, to tell me if this is correct or not, that it seems like, well, if you have if you have a variable, an additional variable measured before the treatment and the outcome, it might initially seem harmless to say, well, let's just also adjust for that one. We're just adjusting for more stuff. But if it ends up being an M, it could make it worse. It could add bias, basically. Right. It's not necessarily safe to just keep adding more and more things. So on the other hand, it's tricky to know when you're in that case or not. So it's it's kind of like sort of
I want to say some. Also, I should be theoretically some. The paper is more academic. So if I would think about how relevant is this in practice, right? Collider issues, as long as they're not post-treatment variables, so these collider issues are usually not that strong. Right? I mean, there might be situations way stronger, but in general, they're not. Right? As long as it's a pre-treatment collider, right? bias simplification, if you have a large set of covariates and if you don't have a very extreme instrument that only predicts the outcome, and if you remove most of the confounding bias, which often is the case with machine learning methods, so also here the extent of the bias you could get in practice is in general also not too large. But we are just started looking at simulations to see how big the bias actually can be under different settings. Because most data sharing processes, when machine learning methods are evaluated, they just use a multivariate distribution. They do not superimpose a causal structure on the data generated. So you will have no chance to find any collide issues to begin with because they are non-baked into the simulation process.
That's great. Thank you. Any other questions? Maybe last question here from Betsy.
Yeah. My question is about when you're using the double robustness property for to get good convergence rates from non-parametric estimators as opposed to for double robustness. So I think that's what's happening in Lasso, for example. You're actually using both Lasso models to estimate the conditional distribution given the full set of covariates X asymptotically, not for finite sample covariate selection typically. And then does that, so I guess my main question is whether that changes your the implementation of your criteria where when you need to have both both A and B met simultaneously to get good rates of convergence as opposed to one or the other, or is that already what you're shooting for?
Yeah, there are different questions when we look at doubly biased machine learning. I mean, first is on getting rid of the regularization bias, and that's what they mostly do. So you use a Nyman orthogonal score essentially to deal with regularization bias. But in order then to get the average treatment effect, usually they start with the set of covariates you use for the machine learning process meets the adjustment criterion. So they would assume if you have hundreds of covariates, then you have a good chance that the entire set meets the adjustment criterion. But if this is not the case, but you still might have subsets of covariates that meet the adjustment criterion, but then there's no guarantee that the lassos on either side will actually find the correct boundary, because they might get misled by amplified bias, by some measurement error to covariates, and then you do not get the right set. Even if we work under the oracle property here, there's no guarantee that it will converge to the right sets that will guarantee a double robust consistent estimate.
Yeah, my question is whether I think I just missed this when you were talking about implementing your algorithm. When you have your new double robustness property with S star, that either the outcome or the propensity score model has to be estimating the conditional expectation given S star. Would you, if you were using this for bias correction as opposed to double robustness, would you think about how to meet both of those criteria simultaneously differently from how you're thinking about how to get one or the other, or is it the same thought process?
Yeah, I mean, that's a good point. So ideally, want to determine the S star using some of the lasso on both sides in the outcome model. Then you would anyways do the post class, so you re-estimate the models, but then you would use a star to re-estimate both models to meet then ideally both conditions for the propensity on the outcome model.
Okay, great, thanks. And one other question is whether I think you maybe already answered this, that you haven't thought about efficiency yet. But in addition to CTMLE, there's a literature by Andrea Ratnitsky and Emma Perkovich and some others on choosing efficient adjustment sets from among all the possible adjustment sets for doubly robust estimation. Have you, and I don't know whether they're just choosing a single adjustment set or whether they're allowing different ones for propensity score and outcome models, but have you looked at that at all? Do you know how?
We didn't look at any efficiency aspects. So we are aware of it that there are selection criteria, particularly for efficiency purposes. We only focused on bias here and not efficiency. But that's a good point too.
Thank you. This was super, super interesting. Thanks.
And And I just wanted to add as a last point for full citations of people that, so the CTMLE, it is what I was thinking of, and it's Susan Gruber and Mark Vanderland. It's an idea from, goes at least back to 2010, but I'll send a more recent paper using it. And I also wanted to mention that propensity score, inverse propensity score weighted regression model technique. So that's attributed to Marshall Joffe. So this is in comments to the Kang and Schaefer paper that you cited earlier, that's attributed to Marshall Joffe. Robbins and colleagues describes how it's going to end. Just to put it out there, I can formally sometimes call it Joffe. Okay. Anyway, side thing, small thing. So, great. Well, yeah. So Helen is saying thank you. Let's all thank the speaker one more time. Great.
So do you think right when you said that doubly robust is a good I don't know. I mean, I just naively I might have thought that doubly robust